But a little bit of a reminder of that, we'll talk about Darcy's law. And Darcy's law says that the Darcy velocity is equal to, and we'll come back to this, but is the interstitial velocity or frontal velocity times porosity. It's equal to K over mu times P1 minus P2 over delta X. So this is like flow in 1D. So imagine we had a one-dimensional rock core. We do these experiments all the time in our lab. So if whenever we get back to normal, if you ever want to visit our laboratories, you'll see these core flood experiments where we do these one-dimensional floods and we flow at a certain velocity. I should also say that this U is equal to Q over A. Okay. So let me explain a lot of those variables. So Q is the flow rate. So it's how many cubic feet per day or milliliters per minute that you're flowing. A is this cross-sectional area. So the Darcy velocity is the flow rate divided by area, and that's obviously got units of length per time, like feet per day. So this is the Darcy or superficial velocity. And then V is what's called the interstitial or frontal velocity. And I don't want to talk much about that now, but we'll come back to it. And it's multiplied by porosity to give the Darcy velocity. Now, I will say that different people use different nomenclature for these. I've almost always seen it this way, where U is the Darcy velocity and V is the interstitial velocity. But I believe that Dr. Sharma in his petrophysics class flips the two. So I want you to be aware of that so you don't mix them up in this class. But in this class, U is the Darcy velocity, V is the interstitial, also called the frontal velocity. V is the porosity of the porous medium. We'll come back to that in a couple weeks. K is the permeability. Mu is the viscosity of the fluid. P1 is the pressure here, and P2 is the pressure here, divided by the distance delta X, or L. Right, maybe we should have said L right there. Okay, so that's the length. Okay, now you can write this in differential form, which is minus K over mu dP dx. And a common question I get, and it's a good one, is why is there a negative sign here and there wasn't over here? Well, the reason is because this gradient dP dx is really P2 minus P1 divided by X2 minus X1. So it's, instead of being P1 minus P2, it's P2 minus P1, so you need that negative. So that's minus K over mu dP dx. So this is single phase flow in 1D. Okay. Now what about multiple dimensions, right? So we can have 2 dimensions, 3 dimensions. How do we do that? Well, we can write Darcy's law then as in vector notation. U is the Darcy velocity. I'm going to define what this vector is again. Minus K. This K is actually a tensor, so I'm going to put 2 arrows on top of there. Mu is the viscosity of the fluid again, times the gradient of pressure plus the density times gravity times grad H. Now I'm going to define all of those. Now be careful here. I know sometimes it's hard for my handwriting, but this is P for pressure, that's rho for density. All right. So this is Darcy's law in multiple dimensions, and it could be in any coordinate system. It could be in cylindrical coordinates, and that's common if you flow around a wellbore. It could be in spherical coordinates, which is not something we do a whole lot of in subsurface applications, or it could be in Cartesian coordinates, and we'll just do Cartesian coordinates for now. So U is a vector. Okay, it's the velocity vector. So the velocity can have an x, y, and z component. So I'm going to write it as a vector, and it's really a column vector, but I'm going to write it as like this. It's going to look like a row vector, but I'm going to transpose it. All right. And I'm really just doing that to save some space. But U has an X, Y, and Z component. So it's these three components of velocity. It's a vector. It's a 3x1 vector. The pressure gradient is also a vector. So del P dp dx, dp dy, and dp dz. So if you were in 2 or 3 dimensions, you could have a pressure gradient in one direction, pressure gradient in this direction, pressure gradient in the third direction. And it's probably already apparent to you that if there is no y and z, and you just have ux and dp dx, then we're starting to reduce to what we had for one-dimensional flow. What about the permeability? So the permeability is technically a tensor. Or you can think of it as a matrix. Okay, so that is going to have an x component, a y component, and a z component. But it also might have off-diagonal terms. kxy, kxz, kyx, kyz, kzx, and kzy. Now this permeability tensor is symmetric. What do I mean by that? I mean that kxy is equal to kyx. I mean that kxz is equal to kzx. And I mean that kyz is equal to kzy. So those are all the same. So another way of thinking of it being symmetric is if you turned it on its edge, if you rotated it, then it would be exactly the same. Or, yeah. So that's the permeability tensor. And so it's got 9 components, which is really cumbersome and difficult to deal with. One thing, and you may have learned this in your petrophysics class, that you can always rotate a permeability tensor, meaning that you can rotate your coordinate system in such a way that it becomes diagonal. So you would just have a okay, and these 3 would more than likely not be equal to these over here, but in general, in this class, we will always use a diagonal tensor. We won't be using the off-diagonal terms, and I'll probably leave off the primes. These are zeros everywhere else. Okay, so it's diagonal. And this would be for a completely anisotropic medium. So Kx is different from Ky, is different from Kz. And some medium are isotropic. So completely isotropic, and what would that be? That would be like maybe like loose sand or prop and pack or a box full of glass beads, something like that. Kx would be equal to Ky is equal to Kz. And then sometimes Kx is approximately equal to Ky, but Kz might be less than that. That's pretty common in subsurface media, where we have in the x and the y direction, those permeabilities are about the same, but flow in the z direction, the permeability is less. That's the permeability tensor. So this is I should have put a transpose here on pressure gradient as well. This is a 3x1 column vector. This is a 3x1 column vector. This is a 3x3 tensor or matrix. What about, so viscosity is a scalar. Density of the fluid is a scalar. G is the gravitational constant. And then we got this del H, which is a vector. dH, dy, dH, dz, and it's really a column vector too, so I'll put the transpose on there. And what is H? H is the elevation. So elevation. So elevation is positive as you go up, right? So when we think about the elevation on Mount Everest, that's a positive number. Okay, I should know what the the height of Mount Everest is off the top of my head, but I don't. So, but it's but we talk about a positive number, so many feet. If you go down, like in a reservoir, elevation would be negative. So the reservoir elevation might be minus 5,000 feet. Okay, and this is the gradient of elevation. So because you could have it at an angle. So the elevation might be a function of x, y, and z if you're at an angle. Now, I don't like to write things in elevation, not when we're talking about reservoirs. So I can write this a little differently. Grad P, I'm going to put a negative sign here. Rho G grad D. Okay, so looks almost identical except that I have a negative instead of a positive. I'm using D for depth instead of H for height. So, whereas elevation is positive as you go up, depth is positive as you go down. So the elevation of a reservoir might be minus 5,000 feet, but the depth is positive 5,000 feet. That's why we've got the sign difference there. And so the gradient of depth is partial of d with respect to x, partial of d with respect to y, partial of d with respect to z, again transposed. So these are equivalent forms of Darcy's law in multiple dimensions. And then what next? Well, another way that this is sometimes written is in terms of potential. So we can write this as minus k, and I should have left this as a tensor, mu times del phi. Okay, so where del phi is by definition del rho minus rho g del d, which is a vector. Okay, so potentials can be kind of confusing. It's always been confusing to me, and I suspect it's confusing for many of you. What potential is it's basically a transformation of pressure. It's got units of pressure. It's got units of psi or pascals. But it transforms it to kind of take away the effect of gravity. And what do I mean by that? Well, think of the pressure in a swimming pool, okay, or an oil reservoir. But the pressure is is atmospheric pressure outside the swimming pool, but as you go all the way down to the very bottom of the swimming pool, the pressure increases, right? And that's due to hydrostatic head. That's the rho g grad d. So as the deeper you go, the pressure is going to be higher. What potential says is that in the absence of any flow, like in a reservoir or a static reservoir, like a swimming pool or a static reservoir, the potential is going to be the same everywhere. So grad P is equal to rho GH when everything is static and there's no flow. So when you subtract off rho GH, the potential will be the same everywhere. So in the swimming pool, the potential at the very top is going to be the same as the very bottom of the swimming pool. Or likewise, the potential at the most shallow part of the reservoir is going to be the same as the deepest part of the reservoir. Okay, so that's potential. Okay, we will use potential some. We'll probably use a lot of pressure. Let's see. So one thing I want to show is how this vector multiplication works. So we've got mu these are all the same. I'm just going to look at this last one. So mu is going to be equal to k, which is a 3x3 matrix, divided by a scalar, which is just 1x1, times a gradient potential, which is a 3x1 vector, right? It's a column vector, 3 rows, 1 column. And if you remember from your vector matrix multiplication, you kind of make sure that these two are equal and they cancel, and then you're left with what's on the outside, which is a 3x1 vector. And that's exactly what velocity was. It was a 3x1 vector, had an x, y, and z component. So that all makes sense. that is a review of Darcy's law. So it's single phase flow, and we started one dimension, but then we went into multi-dimensions. What we really want to talk about in this class is multi-phase flow. So we're going to do things like inject water into an injector well, produce oil. In the reservoir, you'll have both water and oil. Or you might have multiple phases, more than 2 phases. You might have water, oil, and gas. So you could have 3 phases. You learned about that in petrophysics as well. So multi-phase form looks a lot the same. So we're going to have, remember we had mu is equal to K, and a minus there, over velocity, over viscosity times grad P minus rho G grad D. That was a single phase form. We're going to correct this for multi-phase. So first off, the phase could be oil or water or gas. We're going to denote the phase by J. So the velocity is going to be different for the different phases. The pressures of each phase might be different, and the densities of each phase will most definitely be different. So we're going to have that. So that's what that subscript indicates. But for multi-phase flow, we're going to have what's called a relative permeability. So this is KRJ is the relative permeability of phase J. So J is oil, water, gas. So it's the phase. Okay, so I think you've all seen this before. And of course, if you don't have gravity, then that goes away. And if it's on 1D, then you're just left with KRJ times the scalar permeability divided by the scalar viscosity times dpdx. And just to make sure you see it there still is a negative sign in front of there. The next question is, can you explain again why we get a negative sign on the differential form? So that's all the way back at Darcy's law. And I'm glad you asked that, because I think that's a common mistake, and it's kind of confusing. So mu is equal to K over mu times P1 minus P2 over delta X. And so let's imagine we're flowing in one dimension. I can draw a little chord there. Okay, and oh wait, I already had that on here, so I'll just bring this back up. That was my other notes. So let's imagine P1 is greater than P2. Well, P1 is greater than P2, and L is the length, then this is all positive, and our velocity is positive. And that makes sense. Our velocity is going that way, and it's positive. But dpdx is really it's a derivative, but it's going to be P2 minus P1 over delta X, or L. And you know, and if you can imagine that if the derivative is the same everywhere, then it's exactly that. But the important thing is it's this pressure minus this distance minus this distance. So it's P2 minus P1 instead of P1 minus P2. So because you flip this, that's why you get a negative sign over there, because negative P2 minus P1 is really P1 minus P2. So I hope that clarifies things there. When we think of a swimming pool, you know that the pressure is going to be higher at the bottom of the pool, right? Every kid knows that, right? They swim down at the bottom and their ears start to hurt. The pressure is higher at the bottom. Why is it higher? Well, there's no flow, so it's or not much flow, so it's not so there's not additional pressure because of that. There's additional pressure because of gravity. So the deeper you go, you get this hydrostatic head, is what we call it. So it's rho GH. So the deeper you go, the higher the pressure. What potential does is it effectively subtracts out that hydrostatic pressure. So potential is pressure gradient minus rho GH, or minus rho G delta, or D, the depth. And so because of that, rho GD is getting bigger as you go deeper, but delta P is also getting bigger, and so they're subtracting each other out. So maybe I'll write that out again and do it right here. So you've got, here's your surface, this is D, you got over here, the pressure over here might be the atmospheric pressure. The pressure over here is rho GD, right? So rho is the density of the fluid, let's say it's water, D is the depth. So the pressure here is higher than there. But the potential is going to be, and actually I should have said P atmosphere, we'll just say P is equal to 0, that'll make it easier, right? So that's the gauge pressure. So P is equal to 0, P is equal to rho GD, but potential is P minus rho GD, and over here it's going to be P minus rho G, and the depth is 0, so here's the depth is 0, this is the depth, so that's times 0. So this potential is going to equal to that potential, and the potential is going to be the same everywhere else. So all the potential really does is subtracts out the effect of gravity. So under static conditions, when nothing's moving, all the potentials are going to be the same. All right. Okay, the next question. So do we have a KRJ term and a K term? This and this. And the answer is yes, we have both. So K is the absolute permeability. Sometimes we call it the single phase permeability. KRJ is the relative permeability of phase J. Now, one of the reasons that might have sparked that question is that there is another way to write this, whereas instead of writing KRJ times K, they just write KJ. So that's the permeability of phase J. But what we normally do is we separate these two. K is just the permeability of the porous medium. It's got units of like millidarcies or darcies or feet squared. You put it in that. And KRJ is a relative permeability, which is equal to the permeability of the phase divided by the absolute permeability. So that is dimensionless. KRJ is dimensionless and is a value between 0 and 1. And we'll talk more about that. Let me now talk about multi-phase flow in 1D. 1D form of multi-phase flow. And it's going to be in 1D, but we could be at some sort of dip angle. So I'm going to draw a picture. And let's say that we have, here's our bottom. This is going to be alpha. This is going to be our dip angle. And we're going to be flowing in this direction. And to give a coordinate system, x, y, and then this would be some sort of elevation z. Okay, so you could do this in 2 dimensions because flow is going as an velocity has an x component and a y component if your coordinate system looked like this. Okay, but we moved our coordinate system, we put it at an angle, so that angle is agreement with our dip angle. So here's our reservoir, but it's at some sort of dip angle. And so it's really just 1D flow, but it's 1D at this dip angle. So you can rewrite Darcy's law in multi-phase as mu j is equal to minus KRJ, that's the relative permeability of phase J, times the absolute permeability. Now I'm not going to put the double arrows on there anymore because this is only 1D, so K is a scalar, it's no longer a tensor. Divided by the viscosity of phase J. Oh, and boy, I should have done that before too. So I should have put the J for viscosity because the viscosity of oil and water and gas are all different. So we got a viscosity of phase J times the pressure gradient. We're only in one dimension, so it's partial of P, pressure, J with respect to X. So we're going here in this X direction. But we do have some effect of gravity. So this is the density of phase J times G times the sine of alpha, right? I put theta there, that's what that was, but that's the sine of alpha. Okay, and let's think about this. If alpha was 0, if it was 0, then it would be flat. And then the sine of alpha would be 0, and then you'd have no gravitation. So this would just be the 1D form without gravity. If theta were 90 degrees, then the reservoir would be completely vertical. The sine of 90 would be 1, and then you get this effect of gravity, because then, if you're trying to flow upwards, then gravity is working against you, and so you got to account for that. So this is the Darcy's law in 1D, and again, for two-phase flow, you could have UW and UO, where J is equal to W and O, right? Water and oil. And you could have three-phase, you could have gas as well. Okay, now one thing is that you notice I put the subscript J on pressure. That means that there's a water pressure and an oil pressure. And if you have gas, there's a gas pressure too. So what I'm implying is that the pressure of the water and the pressure of the gas at the same location are different. And in general, that's true. So in general, PW does not equal to PO. That's what we call capillary pressure. So PC is a function of the water saturation is equal to PO minus PW. And likewise, dPC dx is equal to dPO dx minus dPW dx. I'm just taking the derivatives there. Right? So this is something that you learned in petrophysics with Dr. Sharma, is that the water pressure and the oil pressure are in general not equal. Their difference is called the capillary pressure. The capillary pressure is a function of saturation. You can take the derivatives of those as well. Now, I will say something right now, is that even though the oil and water pressures are not equal, there are many times where we can ignore their difference. In many reservoirs, the capillary pressure might be a few psi, 1, 2, 3 psi, something like that. Whereas the reservoir pressure is thousands of psi. So the 2 psi is small compared to 5,000 psi. Maybe we could just make the approximation that PO is equal to PW. We'll do that a lot in this class, but in general, that's not true, and there'll be times where we don't ignore capillary pressure. You learned in your petrophysics class that this capillary pressure, PC, which is PO minus PW, is a function of water saturation. And a lot of times we talk about our limits. So SWR, that's sometimes I call that the residual water saturation or the irreducible water saturation. That is the water saturation that we won't go below. So the way a reservoir is normally formed is that it's full of water, and then oil migrates from source rock to the reservoir, and it displaces the water. We call that a drainage process because the reservoir is initially water wet. Oil is displacing water, but it doesn't displace all of it. Okay, even over geologic time, hundreds of thousands, millions of years, it doesn't displace all that water. What's left is SWR, which, by the way, is due to capillary forces. It's due to interfacial tension and things at the small scale. So you won't be below SWR in general. And so I'm going to draw a dashed line over here. We won't go to that. And then on the other end, you could go all the way to 1 over here, but here this is 1 minus SOR. So if then all of a sudden you started injecting water and water displaces the oil, you wouldn't get all the oil out. Some of the oil is left behind. So that's going to be a big theme of this class, is that no matter what we do, there's going to be oil left in the reservoir. And so I'll draw a line right over there too. So if you talk about the process of drainage, where the non-wetting fluid, for now we'll say it's the oil, is displacing the wetting fluid, the water, you'll get something that looks like this. This will be very high, and then it'll come down and look like this. And this capillary pressure is called the capillary entry pressure. We need to overcome that capillary entry pressure in order to drain. Okay. Now the other process is imbibition, which is the wetting fluid, we'll say water, is displacing the non-wetting fluid, we'll say oil. That looks something like this. Okay. I don't want to talk too much about capillary pressure today. I think you learned a lot about that in petrophysics, and we'll return to it. But I really want to talk about relative permeability. So relative permeability I'm going to use KRJ. So R stands for relative, J is the phase, oil, water, or gas. It is defined as the permeability of a phase divided by the single phase permeability, K. So that's the phase permeability divided by the absolute or single phase permeability. Both this and this have units of permeability. Darcy's, millidarcy's, feet squared, meters squared. But since they're both of that, this makes this dimensionless. So that is dimensionless. And it is always a number between 0 and 1. Okay, you can't have negative relative permeability. You can't be greater than 1. And that makes sense because you wouldn't expect the permeability, you wouldn't expect it to be easier to flow once you start adding extra fluids, right? They actually hinder the flow. In fact, we can say that KRW plus KRO plus KRG is going to be less than or equal to 1. It's also a function of saturation, SW. So, again, these are all going to add up to 1 or less than 1. And what a typical plot of relative permeability looks like. Now I'm going to stick to oil and water, no gas, and we'll do that for much of the semester. Talk about two-phase flow, oil and water. If we make a plot of KRW and KRO versus SW, then again, we got some special values on there. One of them is the irreducible or residual water saturation. The other is 1 minus the residual oil saturation, and that's going to be less than 1. This is, of course, 0. Okay. This is 1. And I'm going to say that this is a water-wet medium for now. And if you're a water-wet medium, then what happens is that the water occupies the smallest pores and is kind of cling to the rock, and so you got these films on the rock, and that's where the water is going to lie, in the small pores and right around the rock grains. The oil is going to be in the biggest pores, and the biggest pores are the most permeability. The small pores don't contribute much permeability. So if you have water and oil together, oil is going to be in the big pores, and water is going to be in the small pores. So at the same, at a large oil saturation, the permeability is still going to be very high because the water that's occupying those smallest pores aren't going to affect much. But when the water saturation is high, the oil is still going to be occupying the biggest, most permeable pore, so it's not going to be very much. And the relationship for these is going to be very nonlinear. So what you'll see is that the water relative permeability will look something like this. And this number is going to be a lot less than 1. This is the water rel perm. So this is KRW. And this point right here, where SW is equal to 1 minus SOR, is KRW naught. That's the endpoint relative permeability of water. Endpoint means if you were to inject water and it were to displace all the oil you can, you wait for late times, the relative permeability would be that. That's going to be a small number. It can be like 10%, maybe like 0.1. So that means that even though you've produced all the oil you can and you've got mostly water in there, the water relative permeability is going to be a lot less than that. This number could be like 80% water saturation, but only 10% water relative permeability. The oil, on the other hand, might look something like this. Come up over here. So, okay, once you get to residual oil saturation, it's not flowing anymore, so that's why relative permeability is 0. But over here, this is Kr naught. That's the endpoint relative permeability of oil. That number can be actually quite close to 1 in a water-wet medium. And it's for the reason I just mentioned. It's because in a water-wet medium, when you've got mostly oil, again, let's say that this number is, well, I'll say 15%. Let's say the irreducible water saturation is 15%. That means we have 80% oil. Over there, that 85% oil is all in the biggest, best pores for the best permeable thing. So the relative permeability is almost 1. It's almost unaffected by the water that's present because the water is in the smallest pores. Likewise over here, when we have mostly, so we'll say this is 80% water saturation, even though 80% of the rock is being occupied by water, the remaining 20% that's oil is occupying the biggest, best 20% of the pores. So this number could be quite small. So it could be 0.1, 0.2, 0.3, something like that. But this is what a typical relative permeability curve looks like. And if you were to add up KRW and KRO, they're always going to be less than or equal to 1. Good question here. So I thought gas and liquid permeability differ due to the Klinkenberg factor. For gas, what would be the absolute perm be to calculate the relative permeability? Okay, great. So the question has to do with absolute permeability. We'll just talk about single phase flow. And there's a few different ways I can answer this. The first is that a lot of times we use the term absolute permeability and act as if every rock has its own permeability. In reality, no matter what fluid you inject in there, whether it's water or oil or gas, you'll get a slightly different permeability. And that's why some people like to be very specific about it and say, this is the single phase permeability to oil or single phase permeability to water. Okay, that's the first thing I'll say. But a very good question was asked about gas in particular and the Klinkenberg effect. So again, you all learned about the Klinkenberg effect in your petrophysics class. And so what you learned is that because of slippage at the pore walls, when you have a gas, the permeability can be much different than what you would get from a liquid flow. And that's true. A way to correct for that is to measure the permeability at different pressures and extrapolate to do that. So, if you were to plot permeability of a gas, G, versus 1 over the pressure, and I'm going by memory here, so I hope that this is right, but I know it's basically right. What you'll get is, and you vary the pressure, you'll get kind of a straight line that looks like this. And so if you were to measure the permeability at these pressures, you would get the wrong permeability. But if you extrapolate here, this is K. And I should know. I can't remember if this is K or 1 over K, but it's basically something like that. You vary the pressure, and if you go to high enough pressures, like reservoir conditions, then you don't have very much slippage. And then the permeability, so if P is high, then 1 over P is small, and then you're over here, and this is this. But you're right, if you're doing this experiment in the lab at ambient conditions, you get something smaller.